So this is a short video just to back up video number 2 on this topic. So video number 1 on the reactivity series covered the actual reactions of the metals with common things like water, acids, oxygen. So you could actually see the observations and see for yourself how reactivity actually changed as you went down a group, okay, or from one group to another. The second video then covered the reasons why group 1 metals became more reactive as we descended the group. And this short video just backs that video 2 up, which now talks about why, as we move across a period, so from a group 1 metal into a group 2 metal, okay, in the same period, why that reactivity changes. So let's get on with it. Let's have a look at and see what the reasons behind this are. So the first thing we probably should do here is just remind ourselves as to what actually happens whenever a group 1 or group 2 metal reacts. And the key thing is that they both will have electrons being lost. The whole principle is that electrons are lost and they will end up with a full outer shell. Okay, so if we took this forward, let's take two things in the same period. So let's take sodium, alright, and it makes sense that we would compare sodium to magnesium because this trend from group 1 to group 2 of metals in the same period stands for sodium, magnesium, potassium to calcium, and any of the group 1 to group 2 metals that you might be asked about in an exam question. Right, so let's see what happens to these. They start off at 281, of course, for sodium, and they start off at 282 for magnesium. That will then mean that will go to, of course, 28, and the magnesium will go to 28 also. Now, if we wrote this as ionic half equations or redox half equations, which you will be asked to do, we would represent this as sodium, starting off as sodium solid atoms, goes to a sodium ion, okay, and an electron, which is now seen to be free from the sodium, so it's separated by a plus sign. Likewise, over here, our magnesium, we know that group 2 loses 2 electrons and become 2 plus ions. State symbols aren't really important here, to be honest with you. Okay, and 2 electrons. So I suppose the question is, which one of these is more reactive, and more importantly, why is it more reactive, right? If you think back to maybe the last video, what you've seen in class, you would know that sodium is simply more reactive than magnesium. So group 1 metals, you know, are very, very reactive. And the question is, well, why are they very reactive? This will be what the examiner will want to know from you. Now, there are 3 sort of key main points. 2 of them I'm going to cover first, which are really very much GCSE. And the third one is probably shifting into very star style answer at GCSE, maybe into AS level chemistry. Okay, so in other words, if you're happy and you understand the first 2 points that I'm going to cover, you're probably fine. If you really want to push yourself and extend yourself, you might want to try and get your head around the third point. Right, so let's have a look. And if you think back to the last video, video number 2, the question was, what was it that held those electrons in? Because the more loosely that this electron or these electrons are held, the more easily they are lost, so with less energy in other words, and therefore the more reactive that species is going to be. Right, so if we just really refresh ourselves very quickly, we have our nucleus, which is positive because we have positive protons in it, and we have our outer electron. And we know by now that it is the electrostatic attraction between there and there which holds this electron in place. Now, if we look at a group 1 and a group 2 metal which are in the same period, so for example sodium and magnesium, we will know that sodium has an atomic number of 11, magnesium has an atomic number of 12. That simply means that sodium, from this perspective, has 11 positive charges in the nucleus, whereas magnesium has 12 positive charges in the nucleus. And that's our first reason for the increased reactivity of sodium. Because we only have 11 charges, positive charges here, attracting the outermost electrons, that means that outermost electron has a lower electrostatic attraction to the nucleus, and if that is the case, that means that it is less strongly held, and therefore that means that it takes less energy to remove it. So that is our reason number 1. Okay, so sodium or the group 1 metal, whichever one the examiner asks you about, will have fewer positive protons, okay? And we mentioned that they are in the nucleus. We don't just say fewer positive protons in the nucleus, okay? Attracting the OS, I'm just writing OS for outer shell. We don't just say the electrons, we make sure, we make it clear to the examiner that it is the outer shell electrons that we are talking about, okay? So less attraction to the outer shell electrons, so therefore, okay, we have a lower, and this is a good word to get in, electrostatic attraction, okay, and that is, of course, it's implied here, but it might do no harm to write it, between the nucleus and the outer shell electrons. Never really imply anything for someone who's marking your exam paper. Always make it completely clear you know exactly what you're talking about. And therefore, finally, I know we're getting a bit much here, but we don't want to leave any ambiguity at all in an examiner's mind. Therefore, there is less, I'll just write capital E for energy required to remove electrons from, in this case, sodium than the magnesium. Okay, so there we go, that's number one. Okay, right, let's have a look at number two then. And if we go back to number two, this is usually the one that students pick up on first, and of course I can see why. Well, what's happening here is in group one we're only having to remove one electron, whereas in group two we're having to remove two electrons, and it makes almost common sense that if we have to remove two electrons, okay, so in group 2, GR2, group 2, we are going to have to remove two electrons, okay, and if you have to remove two electrons, that is going to require more energy. Again, this is all about energy. I just write capital E for energy, than to remove one electron, which would happen in the group GR1, group 1. Okay, and again, if they were asking you specifically about sodium and calcium, you would talk there about your group 2 metal being, or sorry, not sodium and calcium, magnesium and calcium. Group 2 being magnesium and the group 1 being sodium. Okay, right, let's have a look at the last reason. The last reason is probably a little bit beyond GCSE, but I think a lot of you will be interested to know it. Right, so let's remind ourselves, we are looking for how much energy really is needed to remove the electrons. Okay, that's all controlled by electrostatic attraction. Now, we've already said that in sodium we have less protons, so we only have 11 protons in our sodium, and in our magnesium we have 12 protons. We said already that 12 protons should give us a stronger attraction to the outer shell electron. Okay, alright, so if we just represent that as 2 lines versus 4 lines if you like, but there's actually something else going on here. Now, if you think about what controls the size of an atom, what is it that, if you think of an atom as being a positive nucleus in the middle surrounded by concentric three-dimensional spheres rather than circles, okay, although circles might do to get the concept into your mind here, what is it that controls the size of an atom? Well, it is the attraction that the nucleus has to these shells, and the stronger the attraction of the nucleus to the shells, well, therefore the smaller that the atom will become. So if I think of magnesium over here, magnesium has got more protons in the nucleus, but it has the same number of shells as my sodium, so they've both got 3 shells, but because magnesium has got more protons in the nucleus, they pull those shells into a smaller volume of space. Now, what does that mean? Well, that means, remember, when we're getting these things to react, it is the outer electron that we have to remove. So the sodium outer electron, not only is it held in by a smaller positive charge, the protons, less protons, it also happens to be further away from the nucleus, okay, and that positive charge. However, because the magnesium has a larger number of positive charges in the nucleus, those electrons, not only are they held more strongly by the 12 protons compared to the sodium's 11 protons, but those outer shell electrons are actually closer to the nucleus. So they're even held more strongly than you might originally anticipate. This is a thing called atomic radius, and I would like to think the term atomic radius is a fairly self-explanatory term. It is the distance between the center of the nucleus and where that outer shell electron hangs out. So in magnesium you have a lower, so in magnesium the outer shell electron, okay, so we write OS electron, is also closer to the nucleus. Okay, we might even write, just to really emphasize there, the positive nucleus. Okay, so that is because it has a smaller, this would be a really good word to throw into a GCSE answer, a smaller atomic radius. Okay, so those are the three, sorry, I should say smaller atomic radius. Always make a comparison than sodium in this instance. Okay, so the other one you're likely to be asked for would probably be potassium versus calcium. I can't see them straying outside that sort of sodium magnesium or potassium calcium pairings of group 1 to group 2. Okay, so that pretty much covers all of that, and you'll see that in your notes. There's a question sheet in your notes which talks about the comparison between group 1 and group 2, as well as the trend going down group 1. By the way, the trend going down group 1 in terms of reactivity is the same reasoning as the trend going down group 2. Both of them increase in terms of their reactivity. Okay, hopefully that helps and explains everything for you.